I look at those, so what do you know then about those two angles that are left over? Based on their location to one another and the parallel lines, those two angles are what? Good, they're same side interior angles, so they're going to be supplementary. So we're going to write 4x plus 2y plus 50 equals 180, right? Now, in all situations, in all mathematics, and you spent a lot of time last year doing this, you should clean these equations up. Okay, so when I clean this up, I would probably prefer to write this as that. Does that make sense? Just move that 50 to the other side. But I get two variables, right? So if we get two variables, we need to use the idea that we talked about the other day of creating a second relationship that hopefully has the same two variables. Or maybe, if we're lucky, maybe we could find another equation that has only one of those variables, because then that will be really easy to solve. Okay? But here, if I look at those, are those two angles very similar to what we just had? Are they still on the same side of that transversal and on the inside or interior of those parallel lines? So those are same side interior angles again. So if they're same side interior, what are they to one another? Take 4x minus 2y plus 70 equals 180, right? Angles that are same side interior should be supplementary. So does everybody see kind of this picture here that we've been talking about for a couple days now, right here? And those two angles are on the inside, and they're on the interior, and they're on the same side. So I would clean that up a little bit as well. So I get 4x minus 2y equals 110. And now the hope is that we realize, well, when I have two equations that have the same variables, I can group those as a system, and I can add them together. Okay? And the hope is that when I add them together, either my y's or my x's are additive inverses, meaning that they're going to cancel each other out, right? They're going to add up to 0. So does that happen here? Do my y's cancel out? I get 0y here, right? That's a nice thing. So I get 8x's is equal to, add those together, I get 240. Okay? Now, not every situation is going to be that convenient. Not every set of equations is going to automatically, when I create them, have either x's that are opposites to one another or y's that are opposites to one another. And if they're not, I can manipulate them through multiplication so that they are. This one just kind of skips that step of having to manipulate those equations. So now if I get 8x equals 240, can I divide both sides by 8 and get x to be 30? Okay. Now, here's the thing. And people are always like, well, where do I put it back in? What equation do we put this in to solve for y? And my question to you is, why does it matter? Why does it matter? As long as you have a relationship that incorporates x's and y's, it should not matter. You should be able to plug that into that relationship, or that one, or that one, or that one. Anywhere that throughout your entire problem that you have related x and y inside the same equation, it shouldn't matter to you where you plug it back in. It will get you the right y. The only place that it might matter is if you're trying to be efficient with your time. So my thought is, I'm probably not going to plug it in here because it's more efficient to plug it in right there, because that's a cleaner version of what I just crossed out. So I'll plug the 30 in right there for that x. So we get 4 times 30 minus 2y equals 110. So that's 120 minus 2y equals 110. Subtract 120 from both sides, and then divide. And I should get y to be 5 in that case. So x is 30 and y is 5. Okay, is that all right with that? It's not the only way you could do this. Maybe I'll demonstrate an alternative way to do this question on 15. Okay. Anybody have questions about 15? Because it's the exact same thing. It's the exact same problem. My thought is, initially though, guys, look at, and we could have done this on the last one, because the question is, well, how'd you know to wipe away either the top one or the bottom one, but you never wiped away that middle parallel line? Well, do I have a singular transversal running through both those parallel lines right now? For instance, this transversal doesn't pass through the bottom parallel line, right? Okay. This transversal doesn't pass through that top parallel line. So these angles, there's no relationship between this 120 and this 140. Okay. Over here, in this one where we wipe these away, there's no relationship between the 50 and the 70. Okay. Now you might say, well, yeah, obviously, because those are just numerical. Well, the next question, maybe those are the algebraic expressions, okay, instead of the other two angles being the algebraic expressions. Does that make sense? Okay, so this line here is only a transversal. Well, it's not even, by definition, it's not transversal at all, because it only intersects one of my lines here. Okay, to be a transversal, it needs to pass through both of them, right? Okay, so that's how I knew which ones to kind of hide. So I'm going to hide that one. And then when I hide that one, it gets rid of that equate or that expression. So now what are you going to say between these two things? They have to 180. So 2x minus y plus 140 equals 180. We'll clean that up. So say 2x minus y equals 40. Okay. Two variables, so that's always a problem. So try to find another relationship. What's the relationship between these two? You guys are like super uber quiet, and I don't know if that's because we're just worried that we're going to say something wrong. I don't care if you're wrong, guys. Okay, I'm wrong a lot. Ask my wife. Okay, and you just got to get over that. Okay, so if you're worried about being wrong, just Hunter, have you ever been wrong? Yeah. Okay, have you ever been wrong in interaction with me? Yeah. Have I ever yelled at you for being wrong? No. Okay, that's part of learning, right? You can be wrong. That's fine. What is not fine is being wrong and just being bullheaded about being wrong and always being wrong and not doing anything to fix being wrong. Does that make sense? Okay, so if you guys want to shout out stuff, shout. I would prefer that. I'd rather have 20 answers that are wrong when I ask questions than crickets. Okay, so when we look at these two, those two things are supplementary. Thank you. And you don't have to raise your hands. Okay, I don't like that. I hate that traditional classroom raise your hand, that kind of thing. Just shout it out. So 2x plus y plus 120 is equal to 180, right? Makes sense, I think, to clean that up. So we get 2x plus y equals 60. Is everybody okay with that? Okay, so we've got these two equations. 2x minus y equals 40. 2x plus y equals 60. What do you recognize about the y's in those two equations? Yeah, they're additive inverses right away. Their coefficients are additive inverses. Okay, so right away, if I take this one and that one and stack them, I'm going to get 4 x's. Those drop out, they eliminate, and I get 100, right? So x is 25 then. Well, if x is 25, let's think about plugging in maybe right here. Doesn't that give me 50 plus y equals 60 when x is 25? So then y has got to be 10. Okay? I know, and there's absolutely, at this point in your lives, there's nothing wrong with this. I know that people are on different levels with this system of equations process. Okay? It's unavoidable. It's the way the questions are going to be written. You're going to see them on end-of-course exams. If you need more questions that are just simply, how do I solve a system equation? You can come down to this block on my website, click on Systems Equations. I don't know if I've shown you guys this or not. And I'm just going to kind of zoom out here so we can get, I don't know if there's a column here that has videos in it. No, guess not. If I look at these, so this is systems equation using elimination by altering equations. Now, some of those you might alter both equations. Some you might only alter one. This is system equations using strictly substitution in this column. So you can go through these videos and you can pick up on the practice, the process, so that when we then have to apply that inside our geometry, that it's instinctual. We know how to do it. Okay. Hopefully, maybe some of us are using those resources. I think that's beneficial. Okay, so there are some other things we could do. That you don't have to ever use elimination. If you're a person that says, I suck at elimination, you can always use substitution. Either method will always work. Does that make sense? Okay, it's just that if I'm going to pigeonhole myself in on this one to use substitution, it might take longer than what elimination does. Okay, so that's why they teach those two techniques. I want to look at question 13 real quick, because I think this is a common issue with questions that do this. I think a lot of people right away, just because of our exposure so far to these two angles, are going to say that those two angles are supplementary. Anybody agree with that? Okay, so I get 10x plus 8y plus 2 equals 180. Okay, we've got supplementary angles there, but that's two variables. So maybe we look at, just real quick, what would be the argument between that angle and that angle? They're the same. They're alternate interior, right? So I get 10x equals 25y minus 20. So now here's my thought. So do I have two equations that have two variables in them? I could have a third. Let's put a hold on that third one though right now. Because if that's enough, if I have two equations, those are different equations, this is enough to do substitution. So I could blindly, without thinking, Scott was saying there's a third one, and the third one should be easier, right? There's a third one, but if I don't see that, I still have the tools to solve this problem. Now, think about how maybe you would solve this. I've had people in the past, and just every year that we've done problems like this, is that they'll say, well, I remember from algebra, in order to substitute, I need to figure out what x is. So divide this by 10, divide that by 10, divide that by 10. I'll put x equals, so this is divided by 10. They put that 5 in it, so it gives me 5 halves. Y minus 2, right? Does that make sense? And they say, okay, well, now I know what x is. Now I come up here and plug x in right there. So I'll have 10, and I'll put 5 halves, y minus 2, and then plus the 8y plus the 2 equals 180, right? Is that perfectly fine to do it that way? But what's going to happen when I distribute that 10? Isn't it going to make that thing right there turn back into that thing right there? I divide it by 10, and then I'm going to multiply that 10 back through after I substitute. That doesn't make, in terms of being efficient, a whole lot of sense. So here's the idea. You were taught, because the hope was, you got to kind of think about and this is, it's frustrating, because I was a student that thought this way as well. I need things to be explained to me, maybe the first couple times, okay? In Algebra 1, you were taught how to substitute. X equals 5 halves y minus 2. Now, everywhere I see x, I can replace that, right? But then you do problems like that for a couple weeks, couple months, whatever. You're never taught then that, well, it doesn't just have to be x that you substitute, okay? As long as the two things that you're taking out and replacing are the same, you should be fine. So instead of taking out this x only and replacing it with 5 halves y minus 2, why not take out the whole 10x? The tablet died. Why not take out the whole 10x and replace it with 25y minus 20? Does that make sense? You can do that. There's nothing wrong with that. It's going to give you the same result that you need. Okay? So that's maybe, if I was going to use a system here, I think that's the best approach. You use substitution there. Okay? It allows me to do it the quickest. Skylar's saying there's one more relationship here, and this is the idea of trying to exhaust all the relationships that you know. What is the link between that angle there and that angle there? They add to 180. And now I'm going to look at those because when I add them up, how many variables are left over? Just one, right? And I can solve for y. I can get my value for y. I'll let you guys do that. But now that I've solved for y, can I come back up here in these two equations and plug it in and solve for x? So even though you didn't use the top two equations to solve for y, you still need one of those to get x, right? So write down all your relationships that you need, figure out which one's going to be easiest to solve. Maybe sometimes you'll get like this, where we got one linear equation, we can solve it. Okay? Other times you might have to pair them up with a system and solve that way. Are there any others on here that you guys want to talk about? Did somebody say 10? All right, let's do 10. Parallel line, and that guy's our transversal, right? So what is the relationship between that angle and that angle? They have to 180. So I got x over 2 plus 7x equals 180. Now this equation is different than a lot that we've seen so far because it's got a fractional coefficient, right? Whenever you have equations that have fractions in them, what you want to do is try to get rid of those fractions the fastest, right? Now you can do this one of two ways. You can look at the left-hand side, and you can merge, you can come with a common denominator on the left-hand side, get one fraction over there, equals 180 as one fraction. You can use a proportion, cross multiply, all that garbage. You could do that. It's not the best, most efficient way. The most efficient way is to multiply, when you have fractions, multiply everything by an LCD. Least common denominator. Basically what that means is figure out what all your denominators are and say, okay, what is the smallest value that I can make all of those grow to through multiplication? So can I make all those get to 2 through multiplication? Yeah. Okay. So what I'm going to do then is I'm going to multiply by that LCD. Now, obviously, the more fractions that you get in your questions, the more complex the LCD becomes. I'll multiply this one by 2. I'll multiply this one by 2. I'll multiply that one by 2. And what happens is I get 2x over 2. I get 14x over 1, and I get 360 over 1. And that should be an equal sign. And now most people don't write it this way, because 2x over 2 is the same thing as what? What's 2 divided by 2? Yeah, that just gives me x. So most people just write it as x. But I wanted to show that what I'm doing, I multiply it by 2. I'm just making this equation twice as big. Okay? But if I make everything twice as big, it does two things. It maintains the same solutions, but at the same time, it also gets rid of fractions. Okay? So now how many x's do we have there? 15 x's, right? Equals 360. So 6, 4, 24, yeah. Yep. Okay. So that quick math there, what I was doing is, I know 15 times 6 is 90. 15 times 6 is 90. I know 360 is divisible by 90 by 4. So then I take the 6 times 4 is 24. So you divide that out, you get 24. Okay? You can check that. Plug it in. Plug 24 in right there, you get 12. Plug 24 in there, you should get 168. And that grouping of 12 and 168 should then model the 180-degree supplementary aspect. Okay? So here's a question, just kind of piggybacking off of the algebra there. If I have 2/3 x plus 1/5 equals 2/4. Okay? My LCD, so here's the idea of an LCD, guys. I'm putting 3. Yeah, the best. Do it this way. I was thinking about getting Excel open, but it'd probably be quicker just to write this down than to open that program. If I start with 3, and I just want to go through multiplication, okay? I want to think about the first number that all of these are going to get to, okay? So if I multiply 3 by 1, gives me 3. If I multiply 3 by 2, 6, and then 9, and then 12, and then 15, and then 18, 21, 24, 27, 30, right? I'm going to do the same thing with 5. Multiply 5 by 1. Multiply by 2. 3. Okay, so if I do this, right here we notice that 3 and 5 both grow to 15 at some point, right? That would be the smallest value that they both grow to. So that would be the LCD between 3 and 5. Okay? But now we've got this fourth thing over there. We got this, this third thing over there, which is 4. And I've got to see what it grows to. So that's 4, 8, 12. So here's the idea. Well, 3 and 4 both grow to 12. So that would be a common denominator, an LCD between 3 and 4. Does that make sense? But I'm looking for the first number that shows up in all 3 of those lists. So I got to keep going. So 16, 20, 24, 28, 32, 36, 40, okay? And nothing's showing up, right? Okay, so what we find out is that I'm going to have to take this out to 60 to do that, okay? But the first number that would show up in this list, in that list, in that list that is shared by all 3 would be 60. What's the fastest way to figure that out? Instead of writing this list down. I take the factors of 3, which are just 3, the factors of 5, which are just 5, and the factors of 4 are 2 and 2, right? Okay? What I need to do is I take each factor, each new factor, like 3, 5 is a new factor, 2 is a new factor, but if a factor repeats itself, I take the one that has the highest exponent. So 2 repeats itself twice, right? So I take 2 squared. So I take 3 times 5 times 2 squared. If I multiply it together, it gives me 60. Does that make sense? So the LCD, instead of making those lists there, the best thing to do is go through and multiply everything here by 60. I multiply this by 60, multiply that by 60, multiply that by 60. Okay? I'm making the equation 60 times bigger, but I make all parts 60 times bigger, so it will still work. It will give me the right answers. Say again? I want the 2 squared. Not the whole thing. I'm sorry, not the whole thing squared. Just that 2, that factor that shows up twice. And that's because, obviously these will both get to 30, but this one doesn't get to 30, right? So I need that extra factor of 2 so they all get to 60. But if I multiply all these by 60, then these fractions will all disappear. Okay? 2/3 of 60 is 40. Okay? 1/5 of 60 is 12. Okay? And then 2/4 or half of 60 would be 30. Would you much more prefer to solve 40x plus 12 equals 30 than 2/3 x plus 1/5 equals 2/4? No fractions in 40x plus 12 equals 30, right? Okay. And then those are little things, guys, and I know hindsight's 20/20, but my hope is that we realize, or we think, especially if we're struggling with the algebra, back to how we operated last year. How did I operate in Algebra 1 class? Did I just kind of shrug things off and think they weren't all that important? Because now I think for the first time, maybe you're realizing how important a prerequisite course might have been for you. Okay? And my hope is in that you realize, okay, well, if I shrugged that stuff off last year and I'm having problems now, if I shrug this stuff off now, think about how those problems are going to compound for the following course, Algebra 2. Okay? And then how that's going to compound then for college algebra, trigonometry, stats, whatever route you take. Okay? Math courses, I think, and this is no fault to yours right now, but as high school students, I don't think that's brought to your attention fast enough or soon enough until it's too late and you realize, oh crap, I'm a year behind or half a year behind. All right, if we have more questions on that stuff, we can talk about it tomorrow. But I think some of this stuff that we talked about today is going to kind of alleviate maybe some of the issues or just be able to talk about them in a different perspective today. So we're not, what I'm saying is we're not moving away from this stuff. Okay, it's a new section, and there's a lot of so don't when I start showing these slides, I don't want you to write anything down right away. Okay, because there's like 8 slides with theorems on them, and we don't need to write all that stuff down. Okay, because I'm going to show you hopefully how we can condense a lot of these slides down into 1 or 2 statements. Okay, so 3.3 is talking about proving lines parallel. Okay, if I were writing this textbook, I would not have this section. I would not have 3.2 either. Okay, I would merge them to one section, especially after what we talked about in section, I think it was like 2.3 or 2.4. Okay, if you remember back to Chapter 2, we talked about if and only if statements, right? Okay, they're called biconditionals. They were created when a conditional statement, an if-then statement, was true, and then you flip-flopped it if-then statement and became determined the converse. If the converse was true, you could take both those statements and merge them into one statement. And we wrote it as a biconditional using the phrase if and only if. I think this would be a perfect opportunity for our author of our textbook to elaborate on that, to actually apply that technique. But they don't do it for some reason. Okay? Everything in this section is a converse of what we learned in section 3.2. So it's basically taking everything in 3.2 and reading it backwards and saying when I do that, the statement that I read and generate when I read it backwards is a true statement. Okay? So in 3.2, we talked about having to start your if-then statement with if lines are parallel, then I learn this information about or angles, right? If lines are parallel, I get congruent alternate interior angles, I get congruent corresponding angles, I get congruent alternate exterior angles, and I get supplementary same-side interior angles, right? Those were the 4 conclusions when the lines were parallel. Today, we reverse it all. Today we say if we have corresponding angles that are congruent, then what can we learn about the lines? Okay, if you see this first theorem here, maybe it makes sense to write this first theorem. It says if 2 lines in a transversal form corresponding angles that are congruent. So we've got congruent corresponding angles. If that's happening in front of me, then I know that the lines that form them had to be parallel. This is the converse of the corresponding angles theorem that we talked about in the last section. If 2 lines in a transversal form corresponding angles, then the lines are parallel. That is just simply taking the statement from 3.2 and flipping the if and then. Okay? If I were to take the statement from 3.2, now you don't have to write this down, I just want you to kind of listen, because I think it's important, guys. One of the main things that I think benefits people in mathematics and just education in general is to make current connections with previous information, make current connections with future information, okay? Because then it provides you an understanding and a realization of how important that current information is. If we can make those links, so this is what we learned in 3.2. That says if parallel lines are intersected by a transversal, then alternate interior angles are congruent, okay? Or actually, I cut and paste this from the last class and I changed this. So let's go using the phrase that we just talked about. We just talked about corresponding angles, right? Corresponding angles are congruent. So put that, Control C, Control V. Okay, so if parallel lines are intersected by a transversal, then corresponding angles are congruent. That's what we learned in 3.2. You just wrote down in 3.3 that if corresponding angles are congruent, then the lines cut by a transversal are parallel. That's basically what you just wrote down in that yellow box over here, right? Okay. Now, that's fine and dandy. That's great. But in section 2, I think it was 2.4, something like that, we said that if those were both true statements and they're converses of one another, you can condense, I don't know, these 40 words into these 20 words and still have both statements being present. Okay? It says lines are parallel if and only if corresponding angles are congruent. If you understand what that means using the phrase if and only if, it means if you start with lines that are parallel, your conclusion is corresponding angles congruent. But it also means if you start with corresponding angles congruent, your conclusion is that lines are parallel. You can read that forwards and backwards, right? Okay, you can read it. You can start with the things that are left to if and only if, and you get the things that are to the right of if and only if. Or you can start with the things that are to the right of if and only if, and get the conclusion that is to the left of if and only if. Well, if that's the case, then we can actually flip-flop this. So this is just taking this here and putting it on the end of if and only if, and taking this part here and putting it at the beginning of if and only if. So those are two adequate, justifiable biconditionals. Okay? And the reason I want to talk about this is because I think our textbook one fails at doing this. And they fail at kind of working you or kind of pulling you along through this structure of statements and explaining what they mean. And they don't use them enough early on, but eventually towards the end of the textbook, okay, and intermittently throughout the other chapters, they'll throw in an if and only if statement and expect that you understand how to interpret it. Well, if we talked about it at 2.4 and don't talk about it again until chapter 7, okay, you might completely forget what an if and only if statement is, right? So as we can see them and develop them, we're going to do that, because then when we get to chapter 7 and we see an if and only if, it's instinctual. You read it and say, oh, I have to absolutely know how to interpret that and how to apply that. Okay? But if we only did that in 2.4 and then chapter 7, we got to have that complete discussion again. Okay? I think math textbooks, you know, it's like you got to actually have maybe a course in how you read textbooks, how you read a math textbook, how you read math terminology before you can actually learn the information that is in the statement. So I try to do that as we work through this stuff. So my argument is, and instead of writing all these things down, didn't we say that when we had two lines that are parallel, that are cut by a transversal, that corresponding angles are congruent? Didn't we say also alternate interior angles are congruent and alternate exterior angles are congruent? We said those three conclusions about congruency, right? So what I would do if I were you is I would underline what I just did and say we can interchange or replace with alternate interior and alternate exterior, and get the same conclusion that the lines would have to be parallel then. Okay, so if two lines in a transversal form alternate interior angles that are congruent, then the lines are parallel. If two lines in a transversal form alternate exterior angles that are congruent, then the lines are parallel. I think doing that, writing that one phrase and then saying what things I can replace is much easier, much more efficient than rewriting 3 or 4 separate statements. Have a seat. There's one more statement. Okay, what do we say about supplementary angles? They had to be what? Or not, sorry. Same side interior angles. What did same side interior angles have to be? Supplementary, right? Okay. So I'll put that one up here for you. And maybe you want to rewrite, okay, because it says a little bit different than what the other ones were saying. It says if two lines in a transversal form, same side interior angles that are now supplementary, then the lines are parallel. Then the lines are parallel. So my hope is that you realize that these are the same exact statements that happened in the last section. We're just reversing them. We're coming up with the converses, starting now with the state or the angle is congruent or the angle is supplementary, and that tells us something about the lines. The algebra problems that we see with these are identical. Okay, the wording that they provide us with in the directions is a little bit different, but the way we approach them is still the same. So once you get that finished writing, we'll target a couple more of those. The types of questions you're going to see in your homework are going to be something like this, where they give you the picture. They say 2x plus 9 and 111. They give you the A and B. Okay. Somebody messed my clock up. Your homework is in your email. Due Thursday.
And then, yeah, that comma's in there, and it says it can't be understood right.
So mark this one right. You did that one right. So I just got to give you. You ran out of options here, right? But so that comma just needs to go through there, and then you could use a union here instead if you wanted to. It doesn't have to be a comma.
And then my main question